given a graph of velocity versus time for the runner. So on the y-axis I have velocity measured in meters per second, and on the x-axis I have time measured in seconds. And as you can see, the velocity of the runner was changing over the 16-second time period. In part A of the question, we need to find out how far did the runner get in the first 10 seconds. Now, in order to find that, let's first recall the definition of instantaneous velocity. The instantaneous velocity is equal to dx dt, or the first time derivative of the position. Now, this can be rearranged, and we can say that dx is equal to v dt, which means that x is actually an integral of v dt from some t0 to some t. This means that mathematically, position is an integral of v with respect to time. Geometrically, an integral is an area under the curve. So in this case, if we want to find out that the distance that was traveled by the runner over the first 10 seconds, we just need to find out the area below the graph during this time interval. So this is the area that we need to find out. Well, now because we have rectangles here, so this area is equal to 2 by 4, so this is 8. This big rectangle here is 4 by 8, which is 32. And then this small square here is 2 by 2, so that's 4. So now we just need to add this up. So the total area is equal to 8 plus 32 plus 8 plus 4. And this gives us 52. Now, remember that this axis has units of seconds and this axis has units of meters per second. So when we calculate for the area, we're multiplying seconds by meters per second, and so we should get meters. So when we say this is the area, it's not an area in the sense that it's in meters per meter square, but it's the area measured in meters. So it's the distance. So 52 meters. So that's part A. In part B of the question, we need to find out the average velocity of the runner over the entire 16 seconds time interval. The average velocity, which we can label as v in triangular brackets, or sometimes we would use v with a subscript avg, or sometimes we would say v with the bar on top. So all of these are just the different representations of the average. So the average velocity would be equal to the total displacement divided by the total time. So in this case, the displacement would be the entire area of the entire graph here. So we've already calculated half of it. So this will give us another 4, this is another 8, and this is 2 by 8, so another 16. So the total displacement would be 52, which we've already calculated, it's this red part, plus 4, plus 8, plus 16, divided by the total time interval, which is 16 seconds. So if you do the math, you should get 5 meters per second for the average velocity of the runner. So 5 meters per second. Now note here that I was alternatively using the word distance and displacement, and this is true specifically for this case because, as you can see from the graph, the velocity of the runner was always positive. In other words, it was always moving forward. Had one of these been negative, it would mean that the runner is moving in the opposite direction, in other words, moving backwards. And then displacement and distance are not the same. And this is something we're going to look in the next example.